Okay, so last time we saw how to construct affine ciphers. Um, Today we'll see an example of affine ciphers before moving on to slightly more complicated ciphers. Because in the previous video, I had told that affine cipher is just another type of, not shift cipher, mono substitute of a substitution cipher, and substitution ciphers, as we talked about, can be broken by looking at frequencies of letters. Now, that is a slightly annoying method to automate, but we'll see how to do that too. So, example of an affine cipher. Okay, so let us look at an affine cipher given by encryption ENC K of M is equal to AX plus B, where mod 26, right? Sorry, this should be encryption of X, not encryption of M, since we are doing letter by letter. And for convenience, for example, let A is equal to 7, B is equal to 2, and my N is 26. N is equal to 26. And so the cipher I am looking at is encryption of X is equal to 7x plus 2. Okay. Now suppose I want to encrypt the word crypto. Want to encrypt the word crypto. CRYPTO. Then how do I do this? Well, I write down the numbers for each of these. CRYPTO. The numbers with respect to this are 2, 17, 24. P is 15. T is 19. And O is 14. OPQR. Yes. Okay. And now I hit all of these by my 7x plus 2. 2 times 7x plus 2 gives me 7 2 is 14 plus 2 is 16. 17 into 7 plus 2 modulo 26 after calculation is, what was it? 17. I'm just going to write these down. I'm not going to compute them in front of you because I did this before. 15 goes to 3. 19 goes to 5. And 14 goes to 22. And so the word I'm going to get from this is QRODFW. Okay, so this is my encryption of the word crypto. Encryption under CRYPTO is equal to QRODFW. Now notice that the letter R went to the letter R. 17 went to 17. And that's okay. It can happen. As long as the entire thing is encrypted, we should be fine. Now, we want to undo the cipher. And the decryption for this, decryption of K of X, is A inverse of X minus A inverse B. Right? That is the formula, mod 26. And the inverse of 7, A is equal to 7. Then A inverse mod 26 is actually 15. Okay? And so, therefore, my formula for decryption K of X is equal to 15x minus 15 times 2. Well, 15 times 2 is 32. 30 minus 30 is minus 4. which is just equal to 15x plus 22 mod 26. Okay, so this is the formula that I will be using, and it is now easy to check. If I feed QRODFW back into this, this should give me back the message QRODFW, which is 16, 17, 14, 3, 5, 22. Let us see if these goes back. I'm not going to check for all of them. I am going to do just one or two of them. Let's do 15. Let's see where Q goes. 15 into 16 is 15 into 16 plus 22 is 262, which modulo 26 is exactly 2, and that is going to go to C. R is 17 into 15 plus 22, which when subtracting 260 gives me 17, and so this is going to be R. You can see that all of them hold up, and so this is going to get mapped to 24, 15, 19, 14, 24, 15, 19, 14, if you trust me. And so this is going to be CRYPTO, just as we intended. Okay, so this is an example of an affine cipher, right? However, as we talked about before, the affine cipher is easy to break by looking at the frequency of each letter, right? And so let us look at what is called a polyalphabetic cipher. Okay, so this was a monoalphabetic substitution where we just shift every alphabet, we substitute one alphabet by another. But now let us look at a polyalphabetic substitution. Polyalphabetic substitution. And the most famous example of it is what is called the Vignere cipher. VIG, Vignere cipher. Okay, so what is Vignere cipher? Vignere cipher is similar to the shift cipher, but instead of just moving things by the same letter every single time, we now shift the number, shift the letters according to a key phrase, rather than shifting everything by a number, by a fixed number. Fixed number. What do we mean by that? So assume that my plain text is plain text, PLAIN text. So if I take my plain text to be, let us tell him about me. Tell him about me. Okay? And I hit it with my key, which is cafe, which is cafe. CAFE, CAFE, right? So I am going to encrypt my word, encrypt my message with the word cafe. And so what do I get as my ciphertext? Ciphertext. Well, let us see. My ciphertext becomes T gets moved by 2 letters. So three letters. T U V W. W. E gets moved by 1 letter, right? Because it's A. L gets moved by 6 letters. So F is 6. So L, M, N, O, P, Q, and R. And the next L gets moved by only 5 letters because that's now hit with an E. So you get a Q. And so that's the first very big difference that we are seeing here. Even if my plain text had both the L's, both of them were L's here, both of these letters were the same, these 2 letters are now different. So looking at the ciphertext, it's no longer that the same letter is being replaced by the same thing. My key text, my plain ciphertext does not represent that these are the same letters. The rest of it is going to go K, J, S, F, S, F, E, P, A, Y, E, P, A, Y, P, F, P, F. So even though there are 2 P's here, the 2 P's actually represent different letters. So these 2 P's here, 1, 2, in the plain text, they're actually representing different letters. So in the first look, it looks much more secure than the normal cipher. So first look, much more secure, question mark, than substitution cipher. Monoalphabetic substitution cipher. Okay, and it is in fact true that this is much more secure than the monoalphabetic cipher, and it was considered to be secure with a question mark for a very long time. I'm saying secure question mark because we haven't yet defined what secure means. And so the question becomes, how do we break the cipher, and how do we attack these things? So attacking shift attacking substitution ciphers. Substitution ciphers. Okay, so when I say attacking substitution ciphers, I mean both the shift, all 3 of them: shift, the standard substitution, affine, as well as Wigner. And we are going to look at them systematically. So for the shift cipher, we said that, an improved method of attack is by looking at letter frequency. A method of attack was to look at standard attack, standard SDANDA, or attack on affine cipher, on shift cipher, not shift cipher, substitution cipher, substitution cipher was doing compare letter frequencies in English language, letter frequencies in English language. Okay, and using that you can find it. The problem with this is hard to automate. Hard to automate, right? A computer is not going to be able to technically, let's say, when I say technically, I'm not saying that it is impossible for a computer, but it's hard for a computer to make sense whether a certain phrase that I'm using is an actual English phrase. Hard for computer to figure out if text is a legitimate English phrase. Right? And that is how you attack the substitution cipher. And now here's a better attack strategy. Better attack strategy. EG1 strategy. And which is, once again, it is going to rely on how frequent the letters in English language are, but we are going to be slightly smarter. So as before, associate the letters, associate the letters with numbers 0 to 25, and then let pi be the probability of the ith letter in occurring in English alphabet, in English text, normal English text. So let me just say in normal English text. Okay, so the thing is, I don't know the probabilities perfectly myself. However, they're available online. They're in the book, table 1.2, figure 1.2. Figure 1.2, right? And then what we know is that summation I is equal to 0 to 25 of pi squared is actually not exactly equal to, is very close to around 0.065. Now, this is a really small number, 0.065, yes, but that is what we are going to take when the probabilities of numbers are, even if we assume the probability of every number is 1 over 26, 1 over 25 is 0.04, so this is a bigger number than the number value of each probability of each letter, right? So we are dealing with small probabilities, but this is what we get. Now, what we do is let qi denote the probability of the ith letter in the ciphertext. Now, for small enough ciphertext, it's going to be pretty skewed, but we are going to assume that we have a very big ciphertext. We have a long ciphertext. Okay, so basically, QI is equal to total occurrences of ith letter divided by total length of the ciphertext. Okay. And so now the thing is, the key idea is that if the key is K for a shift cipher, then expect Q of I plus K to be roughly equal to PI. Then expect to be roughly equal to PI for every I. Okay. So now, just to keep in mind, this QI plus K is actually I plus K mod 26, but I'm just going to refer to it as QI plus K. So what we are going to do is, for given every j, you calculate ij is defined to be summation I is equal to 0 to 25 pi times q of I plus j. So the idea is going to be calculate ij for all j in 0 to 25, and then the key K is the number for which IK is closest to 0.065. Okay, and this is a pretty easy way to automate. And so for a shift cipher, you don't need to go through all of them. You just need to check for one single thing, right? So this is how you attack a shift cipher, or even so, not for this does not exactly work for, what do you call, a substitution cipher, because substitution cipher, each K is going to be different, but the substitution cipher, you're anyway using letter frequencies. Now, this attack also gives us, this way of calculating also gives us a good way to attack the Vignera cipher. Okay, so modifying this approach for Wigner cipher. So so now the previous approach doesn't exactly work. Cannot directly use what do you call yes, cannot directly use ij for all j, as the key might be length more than one. I am so sorry. I forgot to mention that in the Wigner cipher, we call length of this key that we are going to use as the block length. So this is block length 4. If I'm using a 5-letter word, it would be block length 5. So if my block length is more than 1, exact computation with ij does not work. However, note, sorry. However, note that if the block length is k, if the block length is t, if the block length is t, then what do you call? What was I doing? The block length is t, right? Then m1 plus t, m1 plus 2t, and so on, are all shifted by the same letter. Are all shifted by the same letter of the key, right? So all of them are going to be shifted by the same letter, and so what we do is we compare, we look at different block lengths. So take frequency calculations ij for these letters, for these letters m1 plus t, m1 plus 2t, and so on, to find the correct key k for, so let me say mi plus t, mi plus 2t, mi plus 3t, for to find the correct key k for the mi plus rt block. Okay, and use this to find it for every single use this to find keys ki for every block to get the total key k1, k2, k3 kt, right? And so the first, everything is shifted by k1. First, everything is shifted by k1. First block m1, m1t, m2t is shifted by k1. M1 plus t, M1 plus 2t is shifted by k1. M2 plus t, M2 plus 2t is shifted by k2, and so on. However, this is This only works if I know what t is. However, this works if we know what t is. The good thing is you can just repeat the calculation for all t's. If we don't know t, do this for t is equal to 1, 2, 3, so on, till you actually get what you want. So um, sorry, let me rephrase this. If we don't know this, do this for t is equal to 1, 2, 3, and so on for m1. You don't even need to necessarily do it for everything. m1 plus t, m1 plus 2t, and so on. The idea is compute it is equal to summation I is equal to 0 to 25 qi squared. For these, you don't even need to do a shift, just compute the qi squared for this. Okay, when we know when t is equal to so this is tau. When tau is equal to my correct key tau, so this should have been a tau. When t is equal to tau, we expect I tau to be equal to the standard frequency of the English alphabet, which is 0.065. For every other t, we expect the letters to be equally distributed. We expect the letters to be roughly equally distributed. Roughly equally distributed. Which is to say, I tau is roughly equal to summation I is equal to 0 to 25, 1 over 26 squared, which is roughly equal to 0.038, which is very far, which is substantially different, substantially far from 0.065. Okay, and so this is an approach that we can use even against Wigner cipher to break it, and this method works for all these kinds of substitution. Frequency analysis works for all of these substitutions. However, that does not mean every such substitution always is really terrible. An example of a substitution which which we cannot break by this is if you try to guess and extend Wigner cipher, you might be able to say, oh, what if I take my key to be extremely what if I take my block length to be extremely large so things don't repeat precedingly? What if we take t to be extremely large, right? The standard issue with this is problem, hard to remember the key, hard to remember the key. And if it is long enough, you are basically at some point just using substitution. So maybe you can do it, but if it's a short enough thing, it's going to be still breakable by computer. One solution that uses a long key, and when I say long, I mean literally infinitely long, is a solution which uses infinite what do you call block length. Block length is shifting everything by what do you call by by a number related to the position. Number related to the position. For example, shift ith letter, ith place by ith prime. By ith prime. Okay. And maybe you can do this by saying that I don't want to shift everything as by always things, but for example, if we were to do this, I would want to shift. Suppose my key phrase is plain text. Plain text is Veni Vidi Vici. Veni Vidi Vici. Okay, and my key is going to be my primes. So actually, let me first see what is the. So this would correspond to Veni Vidi Vici corresponds to 21, 4, 13, 8, 21, 8, 3, 8, 21, 8, 2, 8. And the key that I'm going to be using is going to be all the primes, right? So first one gets shifted by 2, 3, 5, 7, 11, 13, 15, 13, 17, 19, 23. Okay, this is starting to get a little. Let me just write it down slightly more clearly. Veni Vidi Vici. So 21, 8, 3, 8, 21, 8, 2, 8. So the primes are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37. Right? And so this becomes under the map. These are going to go to 23, 7. Let me just write it. 23, 7, 18, 15, 32, 21, 20, 27, 44, 44, 37, 33, 45, which modulo 26 is just 23, 7, 18, 15, 6, 21, 21, 26. So this is 18, 11, 7, and 19. And the text to that, so ciphertext then becomes X H S P G V U B 23 is that right? 44 is 18. So this is S. 11 is what? L H, and 19 is T, right? And so this is now again something that has infinite length, and so this is going to be slightly harder to break. Now, before we talk about is this really secure, let me do one more interesting cipher that we have before we talk about what it means by something to be actually secure and whether these systems are that we are looking at are going to be secure. So we saw Wigner cipher, which was a poly substitution cipher, right? And we saw an affine cipher. Oops. We saw an affine cipher, which was a shift cipher, but with an AX part. So this is going to be similar. This is called Hill ciphers. Hill cipher. Okay. So Hill cipher was discovered in, invented in 1920s by Lester Hill and published in Cryptography in Algebraic Alphabets. And this brought around a revolution where algebra became involved in cryptography. Okay, so here's how we do it. Suppose we have a system. Suppose we have a system system of linear equations. Equations. Let's say z is equal to 2x plus 5y and w is equal to 3x plus 7y. Then in terms of matrices, you can write this as ZW is equal to 2, 5, 3, 7 XY. Okay, and in terms of matrix multiplication, if you're not familiar with matrices in particular, for an n cross n matrix, so m11, m12 dot dot m1n, mn1, so m21, m22, mnn. All of this, when it gets multiplied by x1, x2 dot 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 xn, you get m11 x1 plus m12 x2 plus dot 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 m1n xn dot 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 mn1 x1 plus mn2 x2 plus dot 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 mnn xn. Okay, so that is how you are going to do matrix multiplication. And how do we use it for Hill cipher? So in this case, our message space M is equal to our space of encryptions is going to be Zn to the n, okay, where we are dealing with n cross n matrices, and my key space is equal to space of n cross n space of invertible of certain invertible matrices, invertible n cross n matrices, If you are not familiar with the word n cross invertible matrices, we will discuss it in a couple of minutes. So, and how does the message get encrypted? So a message which is x, which is x1, x2, all the way up to xn, this gets encrypted under the key En of x is equal to m times x. Okay, where this is my matrix M. Oops, I just wanted to change color. This is equal to m, this is equal to x, and then this is equal to m times x. Okay, so that is how we are going to do it. Okay. However, the key to decryption, is the invertible condition on matrices. So what does it mean? Let's see an example and then we'll talk about it. So for example, let n is equal to 26, which is our letters. There is a reason we are technically saying 26 and then doing stuff, because you can actually use more than 26. You maybe want your capital letters and small letters to be different or something, right? So in that case, you label them differently. And I take the matrix 2, 5, 3, 7. Okay. And the message I want to send is plain text. Is Ruth strikes out. Ruth strikes out. Okay. And the which in numbers is going to be 17, 20, 19, 7, 18, 19, 8, 10, 4, 18, 14, 20, 19. And so then this is another block cipher like the Wigner cipher. We encrypt block by block, block by block. Okay, modulo 26, modulo 26. And so the first block gets, the first block is 1720. We hit it by 2537 with 17 and 20, which is 2 into 17 plus 5 into 20 and 3 into 17 plus 7 into 20, which, oops, scroll down. Oh. Which is equal to, after computation, 8 plus 22 mod 26 over 25 plus 10. When I say over, there's no actual over, this is not a fraction, which is equal to 4, 9. Okay, so the first block gets 4, 9. Doing similarly for other blocks, doing similarly for other blocks, I get my ciphertext to be ciphertext to be 4, 9, 21, 2, 1, 5, 22, 3, 14, 6, 2, 22, 5, 11, which becomes E, J, V, C, B, F, W, D, O, G, C, W, F, L, right? So once again, technically this letter and this letter are actually different, right? This is O, and there is no strikes, there is no O in strikes, but these are being mapped. So it's not completely as a direct substitution cipher. And how do you get back the cipher? How do you decryption? How do we decrypt? How do we decrypt? Well, for 2 by 2 matrices, the inverse matrix is given by if m is equal to a, b, c, d, then m inverse is given by 1 over ad minus bc, d minus b minus c a. So in this case, I have 2537, 2537 inverse is equal to -1, 7 minus 5 minus 3, 2, which is equal to 19, 5, 3, 24. Okay, and now if you observe what it does to the first block, I'm not going to do it to everything. First block, it sends 19, 5, 3, 4, 324, 24. When you hit that with 4, 9, which is the first block of the ciphertext, you do get, after computation, to be 1720, which is the first block of the message. Okay, so this works great. Okay, however, the important part is this. Okay, we can only do it with this. Okay, so let me write down some facts about it. In general, only certain matrices work for M. Not every matrix is going to work for M. For example, 2 M is equal to 2, 4, 6, 8 will produce only even numbers in the ciphertext, which means the map will not be 1-to-1, which means map will not be 1-to-1, right? There will be two things that are mapped to the same pair, because whatever happens, there are not enough pairs, right? There are 26 squared pairs that you're starting from of two different letters, and there are only 13 cross 13, so 13 squared pairs of both numbers being even. So our map definitely will not be 1-to-1, and we will not be able to decrypt. So we can only use invertible matrices. What are invertible matrices? Theorem. For n cross n matrices, over Zn, the following are equivalent. A, the map given by M is 1-1. B, the mapping given by M is onto. The mapping given by M is onto, which is to say, if they're equivalent, then 1-to-1 and onto is bijective. M has an inverse matrix with coefficients in Zn, and D, determinant of M is in Zn star. So the determinant is invertible. Okay. So I am not going to show how to do that, how to prove all of them. I'm going to leave 1 and 2 for you. I'm going to actually leave proving the first 3 are equivalent to you. They're not too hard, because if you have an invertible map, then, well, look at the size of the sample space, look at the size of the starting space, you can easily compute it. A to C, left for exercise, will show C same as D. Okay. First, so first this way. If M is invertible, what does invertible mean? Well, it means there is an then there exists M inverse in my proper space, which is a matrix with n cross n coefficients, such that the identity matrix I is equal to M times n inverse. Okay. Therefore, I hope you guys are familiar with determinant of matrices and stuff. One, which is the determinant of M inverse, is equal to, well, determinant of identity, first of all, is equal to determinant of M times M inverse is equal to determinant M times determinant of M inverse. And therefore, determinant of M belongs to Zn star, right? Because if these matrices have all entries in Zn, then their entries, then their determinant must be in Zn, not necessarily Zn star, but if they're invertible, it has to be in Zn star. Conversely, if determinant of M is actually in Zn star, then we can use Cramer's rule. Then we can use Cramer's rule to solve mx is equal to yi, where yi is the vector, with with 1 in the ith position, and zeros everywhere. Doing so repeatedly, doing so for 1 to n, I is equal to 0 to actually n minus 1 to n, not 0 to n minus 1 in this case. I is equal to 1 to n allows us to find, gives us the columns of M inverse. Okay, so the x for each of these actually form the columns of my inverse. Okay, and so that allows me to find the inverse of such a matrix. Okay, I am not going to go into details about how to invert a matrix. You can look that up, or maybe if needed, we will go through it later. For 2 cross 2 matrices, you have the formula. Okay, for 3 cross 3 matrices, things start getting complicated, but you're basically solving for, you can use Cramer's rule. Okay, so stop. Wait, what? %. Okay, great. Whatever. Okay, so are these systems secure? Are these systems secure? SECURE. Well, the one of the biggest question, are these systems secure? The biggest question we first need to answer is, what does it mean by these to be secure? What does it mean by them being secure? So is it sufficient to say that, oh, any attack is going to take a long time? Is it sufficient? Is it sufficient to say any attack will take a long time, like an infeasible amount of time? Is that the only thing? Are we claiming that, oh, a system is secure if and only if we any message that we send cannot be decoded unless you try, like, for example, brute force and just work out through everything, and it should take you a substantially long time to figure it out, right? But think of it this way. Question. Suppose I am sending a code to a command post is sending a code to enemy to the central, okay, to the front lines. Suppose the headquarters, the HQ, is sending a code to the battlefield front lines. The expected code is either what do you call it? Attack CK or retreat RETREAT. Okay, the code is one of the two. Okay, is either one of these systems is any of these systems secure enough to hide the message if the ciphertext is intercepted. So I want you to think about it, and I want you to, not for submission homework, but homework, read what are the read section, what is it called? What is the section? 1.4 Basic Principles of Modern Cryptography. Section 1.4 Basic Principles of Modern Cryptography. In the next video, we will start off with discussing what does it mean by a system to be actually secure, and looking at some parts of how to define a proper system and other things. But I want you to read this section beforehand so that you can follow it. I'm not going to discuss the entire section, but I think it is an important read. Okay, so please do read this so that you get some idea of what we are trying to do.